all the pulley does is it redirects a force. Alright, so level 4 questions, they're usually going to include torque. I'm just going to talk about torque a little bit here. Well, okay, not in this particular question, but the ones that come afterwards. There's only two. Chill, do not freak out. And don't worry, I won't do a Squidward dab on you again. Kids. Anyway, so this here is a bar, and this black thing is supposed to be a pivot, like a fulcrum kind of. So this bar can like swing around. Just if I was better at animation in Google Slides, then I'd be able to do that for you. But it swings around this whole thing, and it's being held in place by this a string. So it's a static equilibrium problem. Alright, so okay. So as always, we draw our force vectors. So this is going to be our free body diagram. So since this is a bar, we always take the middle of whatever object we have to be the place where the force is act on it. So the middle of the bar is where we're gonna put the mg. And since it's connected right at the middle of the bar, this is gonna be a much easier problem. Okay, so the string also applies a t on it, and we're gonna have the theta over there. But be careful. Sometimes they might give you the theta over here. You might have to find the theta over here by, since this is a right triangle, you're going to do 90 minus that theta to find this theta. You can really do it whatever way you want, though, so. Alright, so t, since it's diagonal, we're going to split it into our components. And this is going to be our force resolution diagram. I need some water. Hello and welcome to Search's ASMR podcast. Today we're learning tension and drinking some water. That's the bottle crinkling. How does refreshment taste? Wait, I just ruined it with like a sniffle. Anyways. So, okay, I drew it like that. This is not how I normally do it. I would actually have this arrow over here. But I just had to make space for this little guy over here. So it's t sine theta, as always. That's going to be the y component, and the x component is going to be t cosine theta. So we already have a t sine theta to oppose the mg, but now we have this t cosine theta. Why did I just go back? Okay. But now we have this t cosine theta, right? And the bar isn't like collapsing in on itself, right? So there must be a force that this big bar thing is applying back onto this bar. And I just put Fn. I could have just put F and not have to explain why it's a force normal. But now I'm gonna explain why it's a force normal. I guess it's because the pivot thing, if you imagine it to be a bolt, it has a surface, right? And that's gonna have a force that it applies onto the bar. Anyway, so these two, now we're okay. Now our bar isn't collapsing in on itself. Now we're all balanced out. Isn't that like a perfect opportunity for one of those comic reference, like the Thanos reference? I don't know. I don't know. I'm not a nerd. Okay. Anyways, so since it's at static equilibrium, it doesn't move up or down. So we're gonna have t sine theta is gonna equal mg, and you're gonna have t cosine theta equal fn. So you can solve for t by just either dividing mg by sine theta or dividing the normal force by cosine theta, but that's hard to find. Whatever you want to do, though. Alright. Okay, so moving on, this is going to be slightly harder, and this is actually going to involve torque. So we're going to have some fun. So this is the theta that we're going to, that I'm going to say we're going to be provided, but again, it could be this one, whatever. And it's attached all the way to the end. The force of gravity still acts on the middle of the bar, so mg, I'm still going to place it right here, but tension now acts all the way from the end to over here, right? And it's much bigger right now. Okay, anyways, we're going to split tension, so t sine theta, t cosine theta. That makes sense so far. And we're going to have an fn, and that's going to equal t cosine theta because it's not moving. All right, so let's review some torque, you guys. So torque is represented by this squiggly t, or tau, and it's going to equal the force that's perpendicular and distance from the pivot. So think about a door. You're going to apply a force perpendicular to the surface of the door to open it, and the farther away you are from the hinge, the door hinge, the easier it is to open the door. So torque can be written as F, that's the perpendicular sign, times the R because it's like a radius from the pivot. So if you think, since it's a pivot and there's a rod, if you think about rotating, it's going to be a whole circle, so this is actually going to be a radius. And instead of actually doing the perpendicular force, you could just do F sine theta times R, which is perfectly fine, but I just like to think of it in terms of finding the force that's perpendicular and actually multiplying that by R instead of doing like sine theta or whatever. Okay, so to do torque stuff, you're going to select a pivot point, and that's pretty obvious. It's this black oval thing, and since it's not accelerating, it's not like spinning around, the net torque is going to be equal to 0. So we have just by looking at the diagram, we have two forces, so mg and t sine theta, which act perpendicular to this bar, and these are the ones that will be applying our torque. So since we need R, we're going to find the distance R1. Please ignore the curly bracket and how ugly it looks. But just imagine it being like a perfect little, mg is the distance, R1 from the pivot. Sorry, mg isn't the distance. What am I saying? R1, what? Okay, yeah. R1 is the distance of mg from the pivot. And let's say, oh my god, okay, let's wait for that. So R2, I'm going to set as the distance of t sine theta from the pivot. Alright, and let's move on. So tau, it's going to equal 0, and it's going to equal, so mg, which is the force, so perpendicular force, times R1, times R, so that's R1, minus t sine theta, times R2. Minus because they're both pointing opposite ways, and I guess this makes me consider downward as the positive direction, which, frames of reference. You got this, guys. Okay, anyways, so this is going to be our kind of thing to rearrange, so we can find t. This t, it turns white. I don't know why. But we can solve for this t just by moving this over, then dividing by sine theta times R2. So this is going to be our tension in this problem. Alright? Simple enough. Alright, and okay, we're moving on to the last question. Alright, let's take a deep breath. Okay. So here we have a bar, and it's suspended by 2 strings on each side, 2 cables, let's say. If you've ever seen like the window washers, you know that they stand on like a platform that's suspended by cables. I guess I don't know. I don't think they do that anymore, but I guess they used to. Or you could think of it as like a swing set if you want. Anyways, so let's put some people on there. So this is my friend Tran, and she has a weight M1G. And this is her twin sister Sam, and she has weight M2G. All right, so far so good, you guys. And our goal is going to be to find tension in one of the strings. Let's say we want to find tension in the right string. So first we're going to select this pivot point. Oh, and this is going to be a torque problem, by the way. So first we're going to select a pivot point. And usually you select the pivot point to be on the side of the tension that you don't care about. So we're going to select the pivot point to be here, since we want the tension over on the right side. And so right here we have the tension vector for the right cable. Since it's not accelerating, net torque is going to be equal to 0. So it's not accelerating, so if you imagine taking away this rope completely, they're going to plummet to their deaths. And I don't want that because they're my friends. My beautiful Asian friends, both of them. So they're not accelerating, net torque is 0. So there's a constant force of torque being applied here, and Tran is applying a torque downward, and so is Sam down here. Alright, so torque equals 0. Alright, let's do it step by step. If this stupid okay, so T, the tension here, as you can see, all of these are perpendicular to this bar. Don't skip ahead without me. Okay, so T, if you know, okay, so T is perpendicular force, R3 is its distance from the pivot. So we already have T times R3, and so we're considering upward to be positive here. Next, we're going to have Sam's distance from the pivot, and that's going to be R2. And since her her weight points downwards, it's going to be a negative M2G R2. Lastly, Tran is R1 away from the pivot point, so it's going to be minus M1G times R1. Alright, now that you have all that, you can just solve for T, and it's as easy as pi, and now they're not plummeting to their deaths, and everyone is happy. Alright, and that's about it. Thank you for watching, and Sush will be back with another physics video if you just ask for it. I love physics. I love chemistry too, if you want chemistry. I guess I could do some bio. Math maybe? Yeah, I could do some math and calculus. Bye guys.